Notions of work and kinetic energy, the work-energy theorem. The relation v square minus u square is equal to 2as describes rectilinear motion under constant acceleration, where u and v are initial and final speeds, and s is the distance traversed. Multiplying both sides by m by 2, and using Newton's second law, the equation becomes half m times v square minus u square equal to F, where F is the force and s is the displacement. Generalizing to three dimensions using vectors, v square minus u square is equal to 2ad, where a and d are acceleration and displacement vectors. Multiplying both sides by m by 2, the equation becomes half m v square minus u square equal to F dot d. F is the force vector and d is the displacement vector. The equation motivates the definitions of work, W, and kinetic energy, K, as the change in kinetic energy, delta K, being equal to the work done, delta W. The left side of the equation represents the change in the quantity 1/2 times the mass multiplied by the square of the speed, from its initial value, k_I, to its final value, k_F, in kinetic energy. The right side is the product of displacement and the component of force along the displacement. The work-energy theorem is expressed as the difference between the final and initial kinetic energies, k_F minus k_I, equals the work done, W. This equation states that the change in kinetic energy is equal to the work done by the net force. It holds true for work done by a force on a body over a certain displacement. It is well known that a raindrop falls under the influence of the downward gravitational force and the opposing resistive force. The latter is known to be proportional to the speed of the drop but is otherwise undetermined. Consider a drop of mass 1.00 grams falling from a height of 1.00 kilometers. It hits the ground with a speed of 50.0 meters per second. What is the work done by the gravitational force? What is the work done by the unknown resistive force? The change in kinetic energy of the drop is given by delta K equals minus 0.5 mv superscript 2, where m is 1.00 grams and v is 50.0 meters per second. This calculation yields 1.25 joules, assuming the drop is initially at rest. Assuming that the acceleration due to gravity, g, is a constant with a value of 10 meters per second squared, the work done by the gravitational force is calculated as Wg equals mgh, resulting in 10.0 joules. B. From the work-energy theorem, delta K equals W plus Wg plus Wr, where Wr is the work done by the resistive force on the raindrop. Therefore, Wr equals delta K minus Wg, which equals negative 8.75 joules, indicating a negative value.